Hello, and welcome to the series of videos related to operations research. In this series, we will cover some important concepts and methods related to solving operations research problems. To properly follow the contents of these videos, it's best if you have a basic working knowledge of linear algebra and differential calculus. I hope this series of videos clear your concepts regarding operations research and that it proves beneficial to you. All content used in these videos is referenced from the following two books: Operations Research and Introduction by H.A. Taha and Introduction to Operations Research by Hillier and Lieberman. Before we begin delving into operations research and solving problems, let us first define what operations research is. Operations research, or OR for short, is essentially research on operations. It is a means to determine how to conduct and coordinate activities within an organization. It also deals with allocation of resources to various activities in a way that is beneficial to the organization as a whole. And in fact, if we delve into the history of OR, it was first officially used during World War II by the British in order to determine the best utilization of war materials based on scientific principles. Hence, OR uses the scientific method to investigate a problem and pertains to applying advanced analytical methods to improve decision-making. Therefore, it is based heavily on applied mathematics. In detail, OR uses optimization, probability, and statistics to solve problems in several domains, ranging from engineering to management and industry to public sector. It provides a systematic approach to a problem to get optimized results by making use of mathematical models that break down problems into basic components. These problems are then solved using an algorithmic approach. An algorithm, in simple terms, is a step-by-step method of solving a problem. For instance, the instructions on the back of a shampoo bottle on how to wash your hair, or in a user manual of a cell phone explaining how to add contacts into your cell phone, is an algorithm. Hence, an algorithm is an ordered sequence of unambiguous instructions that is guaranteed to solve a specific problem. In OR, algorithms, which are a collection of fixed computation rules, are applied repetitively to a problem, and each repetition, termed as an iteration, brings the solution closer to the optimal value. Finally, this optimal solution must be converted into a form that provides reasonable conclusions to decision makers when required, in a process known as analytics, which is the scientific process of transforming data into insight for making better decisions. So how is OR relevant to the world today? Well, one reason is the expansive growth in the size and complexity of organizations in a manner that the components of an organization have developed autonomy with their own goals and systems which might conflict with another area of an organization. OR helps avoid such problems. In terms of computer science, operations research is helpful in developing computer segments, modules, or subroutines to solve problems such as caching, routing, dynamic TCP acknowledgement, etc. It is also useful in cryptography, 3D game programming, data compression, social networks, and artificial intelligence problems, to name a few. The OR approach comprises of 5 phases. The first phase is problem definition. This is by far the most important phase of the approach, for if the problem is not well and accurately defined, it cannot be solved. Moreover, if the problem definition is inaccurate, it will be difficult to get the right answer from a wrong problem. Problem definition involves studying the system, identifying the problem area, and then preparing a well-defined statement of the problem. It involves going through a large amount of data which may be relevant or irrelevant or even incomplete, and then identifying the points of interest within the data by refining it. A well-defined problem has 3 principal elements: an objective, which clearly states the purpose of the study, limitations or constraints under which the model or system operates, and finally alternatives, which are course of actions that are available in order to achieve the objective. Once we have identified the problem, we move on to constructing the model of the system. Model construction involves translation of the problem definition into mathematical relationships. It gives the essence of the problem, shows interrelationships, and facilitates analysis. Mathematical models are idealized representations expressed in terms of mathematical symbols and expressions. In other words, they are a system of equations and related mathematical expressions that describe the problem. This means that the modeling phase involves making significant assumptions, and that in fact is intuitively acceptable, for the entire real world cannot be represented by relatively simple mathematical expressions. In fact, during modeling, only a portion of the real world, an assumed real world, is considered by concentrating on the dominant features of a real system. That is, the features which predominantly control and affect the behavior of the system. In other words, abstraction is widely used during modeling. That is, we hide the information which is irrelevant to solving the problem while focusing on aspects of the real world which are useful in solving the problem. While mathematical modeling is an important phase of the OR approach, it is not absolutely essential. In fact, simple, straightforward approaches must be explored first to solve the problem at hand. Nevertheless, the use of optimized algorithms require that the mathematical model be available. A general OR problem model involves the following key components: decision variables, which represent the decisions to be made. If there are n decisions, then xn variables are required. These are the unknowns of the problem. Some examples of decisions include the number of products to be made for maximum profit, the number of workers to be assigned to a task for release cost, and so on and so forth. The next is an objective function, which is a measure of performance, such as profit or cost, that must be increased or decreased based on the decision to be made. Then there are constraints, which represent the restrictions applied to decision variables. Some examples of constraints include the use of a raw material that cannot be negative, generally known as non-negativity constraints, or a limit on the maximum amount of raw material that can be used, or that the number of workers cannot be in fractions, etc. And finally, parameters. These are the coefficients of the objective functions and the constraints. These are generally approximated based on the data available regarding the system. Finally, a general OR model is written as shown here in this block. Once a suitably defined model is available, we move on to determine a solution for it in the third phase of the operations research approach. Model solution involves using standard, well-defined and optimized algorithms to achieve the best solution. This makes it the simplest of all OR phases. However, the type and complexity of the mathematical model essentially dictate the solution methods. For instance, linear objective functions and constraints can be solved easily by linear programming. If the decision variables have integer values, we can use integer programming. Or if the problem can be decomposed into smaller subproblems, we can use dynamic programming, and so on. Furthermore, there are various types of solutions that can be obtained. If a solution satisfies all the specified constraints, it is known as a feasible solution. Likewise, if a solution violates at least one constraint, it is known as an infeasible solution. If the solution is both feasible and yields the best performance measure, that is the best maximum or minimum value of the objective function, it is known as the optimal solution. Now consider a situation where an optimal solution is obtained, but a revision of the model adds another alternative which leads to an even better, more optimal solution. In such a case, the previous solution, which was found to be optimal, no longer remains so, and thus becomes a suboptimal solution. In fact, there may be situations where the cost to determine the optimal solution is too large. In such situations, we make assumptions and ignore certain aspects as long as they affect the solution very minutely and opt for the suboptimal solution. Another important part of the solution phase is the sensitivity analysis. It deals with obtaining additional information about the behavior of the optimum solution when the model undergoes some parameter changes. Recall that parameters are generally approximations. Hence, as the parameter estimate changes, the optimal solution may or may not vary. Sensitivity analysis determines the effect of changing these parameter values on the obtained solution and is particularly useful in cases where parameters cannot be obtained accurately, or in the presence of sensitive parameters, which are parameters whose value cannot be changed without changing the optimal solution. The next phase in the OR approach is model validation. Model validation involves testing the model to determine if it accurately predicts the behavior of the system under study. The results should be intuitively acceptable. That is, the results should make sense. In this phase, the OR scientists identify and correct as many flaws in the model as possible. They ensure that the initial assumptions were correct or modify them, and by extension the model, if they were incorrect. A common model validation technique is retrospective testing, which involves using historical data and comparing the model output with actual historical results. A reasonably valid model is expected to duplicate the past performance under similar input conditions. In this phase, it is also useful to ensure that all mathematical expressions are dimensionally consistent in the units used. For instance, in the speed formula, where speed is equals to distance over time, if the speed is given in kilometers per hour, then the distance should be given in kilometers and the time should be given in hours so that both the left-hand side and the right-hand side are consistent in units. Finally, the last phase of the OR approach is implementation. Implementation involves translation of the results obtained from the validated model into understandable operating instructions. That is, instructions which are relevant and understandable by the organization's management or people who will administer the recommended system. Implementation involves putting the system into operation. Moreover, documentation is also a very important part of this phase, as a clear and accurate documentation of the methodology of the system ensures that the work is easily reproducible.